But the point is that the formula for the z-test proportions is kind of based upon that. So we discussed proportions a while ago, so hopefully you remember a little bit of that. But like it says on here, that is where the formula comes from, is basing it kind of on like a binomial experiment. But I'm okay if you like don't know that. I'm not going to test you on that. So let's go ahead and write down what the formula is for the z-test for proportions. Okay. So it is z equals p hat minus p. And hopefully some of these look familiar. And then p times q divided by n, or the square root of p times q divided by n. All right, well, let's identify what everything is here. So p hat is going to be your sample proportion. And this is calculated as x over n. So if you're like trying to find the proportion of people who, I don't know, proportion of people who like chocolate ice cream, as opposed to vanilla, you would take the number of people that like chocolate ice cream over the total number of people in the population, and that would be your sample proportion. So that's what x over n means. But sometimes you're just given the proportion in a percentage, and so you don't have to do that. P is going to be your population proportion. And then if you would think back to when we talked about proportions, Q is going to be 1 minus P. And hopefully maybe you see the connection here between this and the binomial distribution where we had like P and then Q was 1 minus P. Hopefully you can just see the connection. N is your sample size. And there we go. So that is how we do the z-test for proportions. This is our formula, and this is what everything is. We are given all of these pieces, except for Q, we have to calculate Q as 1 minus P. But yeah, everything should be pretty straightforward in the problems that you have. Like this says, since this is a z-test, we can use table E. So whenever we're doing z-tests, we are using the z-score table, and then whenever we're doing a t-test, we're using that t-distribution table. Okay, so first we're going to do one example with the traditional method of hypothesis testing, and then we're going to do 2 examples with the p-value method. Did I really put 2 examples in here? I did. Okay, I only remember putting 1 in here, but I did. Okay, so we're doing 1 traditional method example and then 2 p-value method examples. So the traditional method is that one where you find the critical value and then you have the critical region and you see if your test value falls within that critical region. And if it does, you can reject the null, and if it doesn't, you can't. And the p-value method is where we calculate the p-value and see how it relates to alpha. And based on that, we can reject the null hypothesis or not. So we're going to do some of each because they're both important, but I prefer the p-value method. But let's do the first example, the traditional method. So this says a researcher claims that based on information obtained from the CDC, 17% of young people ages 2 to 9 are obese. To test this claim, she randomly selected 200 people ages 2 to 19 and found that 42 were. At a significance level of 0.05, is there enough evidence to reject the claim? Okay, so in all of our hypothesis testing problems, we always start out with writing out what the null hypothesis is and what the alternative hypothesis is. And remember, the null hypothesis always has an equal sign in it. So it's always like P equals this, or if you're doing means, it's mu equals this. So for our null hypothesis, we've been doing it with means, so we've been using mu, but when you're doing proportions, we're going to be using P. So the null hypothesis is going to be that P is 17%. Or writing that as a decimal, it's going to be 0.17. And then we're going to write down our alternative hypothesis. And this is just going to be that P is not equal. And the researcher claims that based on information obtained, 17% of young people are obese. So our claim is going to be that P is 0.17. So this is our claim. Okay, so since we are doing the traditional method, we're going to find our critical values using the appropriate table. So we need a little bit of information in order to do that. So we have alpha is equal to 0.05, and we know this is a two-tailed test because we have P is not equal to something, so we know that there can be things in either tail. So that's why we have a two-tailed test. We don't have a greater than or a less than sign. So I'm going to draw out my distribution so we have an idea of what we're looking for. Okay, so two-tailed, so we have both ends that we're concerned with. And since sigma is 0.05, we know that 0.05 divided by 2 is the area that we want in each tail. So we know that here we want an area of 0.025, and same there. And we want to find what's called the critical values, and that is those numbers that are the cutoff between the critical region versus the non-critical region. So if you remember, our critical region is there and also there. Okay, let me open up my table because I don't have it. Okay, so we want an area of 0.025 in both tails. So we need to look at our chart and find the area of 0.025. So let's see. We have, let's see, 0.025 exactly, actually. So that's nice. It's right there. And that corresponds with negative 1.96. So now we have our critical values. So if we come back here, this is going to be negative 1.96, and this is going to be 1.96. Okay, so our third step is to compute the test value. So we need the formula for the test value. So I'm going to write that down. So it is z equals, and this is just what was at the top of the page, p hat minus p over pq divided by n. Okay, well, let's identify each of these things in the problem that we were given. So p hat is going to be the, oh my gosh, sorry, my thing is so weird sometimes with scrolling. Okay, so p hat is going to be the sample proportion. So we can see that it says to test the claim, she randomly selected 200 people and found that 42 of them were obese. So that means that the sample proportion is 42 out of 200. So we can write that down. 42 out of 200, which we want to convert that to a decimal. And if you do that in your calculator, that is just 0.21. We also need P, and P is going to be that proportion that is in our hypotheses. So P is going to be 0.17. It's the proportion that we're claiming about the population, which is 0.17. And then Q is just 1 minus P. Like I said, you're not explicitly told what Q is, but you can just calculate it easily by subtracting P from 1. And that gives you 0.83. And then we also need n, and n is going to be the sample size. And by reading our problem one more time, we see that she selected 200 people, which means our sample size is 200. So now we just have to plug all of this in. So we get 0.21 minus 0.17, and that is all over 0.21 times 0.17 divided by 200. I'm going to plug this all into my calculator. All right, and I got something. Hold on. Oh, because I wrote this down wrong. Sorry. This should be P times Q, and Q is 0.83, not 0.17. My bad, everyone. Let me recalculate this. Okay, so I still got something. Oh my gosh, I wrote both of these down wrong. I'm so sorry. Goodness, okay. P times Q is 0.17 times 0.83. Oh my gosh, I'm gonna get it right at some point. Third time's the charm. Okay, cool. So when you do this, you should get 1.51, and that is going to be our test value. So if you remember, the way we decide to accept or reject the null hypothesis is based on if the test value falls within a critical region or if it falls in the non-critical region. So if we come up here, we have to see where 1.51 would be. And that would be about like here, maybe. So we can see that this doesn't fall in the critical regions. It actually falls in this non-critical region in the middle, which means that we can't reject the null hypothesis. So we cannot reject. Okay, and then just to give a summary to our results, that means that there is not enough evidence to reject the claim that 17% of young people ages 2 to 19 beats. And that's it for this problem. So this looks a lot like things we've done before. It's just there's a different way for computing the test value. There's a new formula because it's proportions. But besides that, the same process and everything holds, and it looks about the same. Are there any questions on this example? Okay. So I have two examples next that instead of doing the traditional method, we're using the p-value method. So I just have two different ones, but we're going to use the p-value method for both of them. So the first one I want to do with you guys and walk you through it, but then I was hoping to have you all attempt the second one yourselves, but I thought we could switch it up and we could go in two breakout rooms. So I thought I could put like half of you in a breakout room and the other half in another, and you could work on it with other people. I don't know if that's something that you guys want to do, or if you just want to stick with my usual method of, hey, work on your own and like private chat me your answer. Like, I don't know if you guys like that. Sometimes breakout rooms work really well and sometimes they don't. I've been in classes where they didn't work well and no one talked, and so it was just like not good. But I don't know if you guys would be interested in doing that. So I would do an example with you and then let you do it with other people, the next one with other people. So I put together a poll. So if you don't want to do it, that's totally fine. I just thought we could switch it up if you guys wanted to. I don't know if you're tired of my usual like method. So I put together an anonymous poll just asking if you want to do an example in breakout rooms or if you would want to do them just like on your own. So I'm just going to launch that poll. So just let me know what you want to do. It doesn't matter to me either way. So it is completely anonymous. Okay, so I only have half the class that's voted. Oh no, I'm gonna need one more person to vote. Well, I need two more of you to vote, but after one, I can conclude which one we're gonna do. All right, I'm gonna give you a few more seconds and then I'm just gonna close it. Okay, well, the majority was to work alone, so that's totally fine. I'm not the biggest fan of being in a breakout room, so I don't blame you all. I just thought I'd give you that option. So let's do this example together and then you can try the next one on your own. Okay. So this one says an attorney claims that more than 25% of all lawyers advertise. A random sample of 200 lawyers in a certain city showed that 63 had used some form of advertising. At alpha equals 0.05, is there enough evidence to support the attorney's claim? Use the p-value method. Okay, so like usual, we're going to start off with at least identifying what the claim is and stating what your null and alternative hypothesis each are. Let's go ahead and do that. So remember, our null hypothesis always has an equal sign. So the proportion that we are looking at is 25%. So this is going to be equals 0.25. And then we need to write our alternative hypothesis, which it's an attorney claims that more than 25% of all lawyers advertise. So this will be P is greater than 0.25. Well, and that's not too hard to identify the claim since it says the attorney claims that this is true. So that means that this one is our claim. Okay, so for step 2, let's compute our test value. Same way we did last time. So our formula is Z equals P hat minus P over the square root of P times Q over N. So let's just identify what each of these things are. So if we look at our word problem, P hat is going to be the sample proportion. So we had a random sample of 200 lawyers, and then it showed that 63 had used some form of advertising. So out of that random sample of 200, we had 63 say they had used advertising. So that means our sample proportion is 63 over 200. And that is going to be 0.315. All right, next we have to figure out what P is. And this is just that number that's used in our hypotheses. So that's the proportion that we're claiming about the population, which is 0.25. And then Q is just 1 minus 0.25, which is 0.75. And then N is going to be the sample size, which is 200 because we did a random sample of 200 lawyers. So to fill this all in, we get 0.315 minus 0.25. Let's see if I can do this correctly this time. So this should be 0.25 times 0.75 divided by 200. All right, let me figure out what this is. Okay, and I get 2.12. So that's what I get for my test value. And when we're doing this using the p-value method, after we figure out what the test value is, our next step is to find the p-value. So let me kind of do a little image so I can explain how to find the p-value again. Okay, so because we got our test value of 2.12, I'm going to say that's about here. And our p-value is going to be this area here. So the p-value, just in case you need a refresher, is that area. Okay, and the way to find that area is to use our little z distribution chart. And if you remember, the z distribution chart gives you the area to the left side of whatever z-score you're putting in. But we want the area to the right side of 2.12. So we're going to end up doing 1 minus whatever that number is. So let's go to our chart. And I'm looking for 2.12. All right, well, 2.1 is down here. And then if we come up here, 0.2 is here. So we have 0.9830. Okay, and if we go ahead and do 1 minus 0.9830, that gives us 0.017. Okay, so what we do with this now is we make our decision to reject the null or not. And if you recall my lecture video, if the p-value is less than the level of significance, or alpha, so in our case, if p is less than 0.05, then we are going to reject the null. And if p is greater than the point, what did I say? Oh, 0.05, then we're going to not be able to reject the null. So see, our p-value is 0.017, and then our significance level was 0.05. Okay, well, our p-value is definitely less than that. So we are able to reject the null. All right, and then lastly, we always just write a nice little closing sentence that summarizes the results of being able to reject or not reject the null. So this means that there is enough evidence to support the claim that more than 25% of lawyers use advertising. And that is it for this problem. I do want to give like a little calculator demo though of how you can find the p-value, and then like I think it also gives you the test value. So I just want to give a little demo of how you can do this in a calculator. If either I tell you can use the calculator on the exam, or if you just want to check your work, that's totally fine. I get wanting to like make sure that you did the calculations correctly. So I want to do a little demo first. But are there any questions before I do this demo? Okay. Let me pull up the calculator here. Okay, so you should be able to see the calculator. So I'm doing this for the second example. This is, okay, I'll show you how to get here first. Sorry, let me clear this out. So you're going to hit the stat button, which is usually how we start these things. And then also totally feel free to follow along while I do this. And I'm not sure if I said this, but at the end of each section, there's in the textbook, there's a little like box that gives you how to do these things in your calculator and Excel as well. So there's like two little tutorials. Like if there's anything in this section that you could do in a calculator, there's usually like a mini tutorial at the end, which is totally how I'm teaching myself how to do this because I did not use a calculator when I did intro to stats. I did it in R. So I know how to program and do all this stuff, but I don't know how to use my calculator to do it. So if you go to the end of a section or you don't remember how I told you to do these things, there's a little tutorial at the end, which is the same way that I'm showing you how to do it. So just in case you need that. So at the end of section 8.4, there would be a little tutorial that tells you how to do this. Okay, so you hit the stat button, and then you're going to come over to the right to test. And we are doing a one proportion z-test. So you're going to select the number 5. We're doing proportions and it's a z-test, and we're only dealing with one proportion. So you're going to hit 5. Okay, I think I actually already entered this stuff in. Yeah, this is actually it, but I'll go through how you do it. So P naught is going to be the proportion that is used in your claim. So whatever is stated in your hypothesis is going to be what goes here. So I put 0.25 because in my hypotheses, I have P equals 0.25. And then in my alternative one, I have P is greater than 0.25. And then you'll come down to here, and X is going to be the number of, like, so when you calculated our proportion, we did 63 over 200. So X is going to be 63. Like X is the number of people out of that sample that said they had used advertising. So you don't have to, when you use the calculator, you don't have to give it that P hat value, which is 63 over 200. That's because the calculator will just do it itself. So you don't have to feed it that, it'll just calculate it on its own. So all you have to give it is 63, and then as well what N is, which is 200. Okay, I think this might be the wrong one. I think it's supposed to be like this. I think it's supposed to be that one. Let me make sure that's correct, really. Yeah, that's correct. Okay, cool. So yes, up here it says that our alternative hypothesis is that the proportion is greater than 0.25, which is correct. So if you put all this information in and you want to make sure, just double check the things that it's telling you at the end. So our claim was that the proportion was greater than 0.25. It also tells you the test value. So it tells us Z is 2.1228911. Obviously, we just got 2.12 because we rounded, but there's our test value. So if you ever want to check and make sure you calculated the test value correctly, here you go. And then this will also give you the p-value, but you'll notice that our p-value, we got 0.017, where here they get 0.0168. Yes, that would round to be 0.017, but I just wanted to say that the reason that they might get a p-value that's slightly different It's because when we're going to our z table with our value of 2.12, that's obviously rounded. You can see their z value isn't rounded, so their p-value has like more digits at the end, which means it'll probably be a little more accurate. So that's why there might be a slight discrepancy between what your calculator gives you and what the table gives you, but that's just because they go out to more decimal places. Obviously, when we're using our little chart, we can't go out to like 8 or 10 decimal places. It's only rounded to a few decimal places because it's just not practical for a chart to go out to that many decimals. So you might notice a slight difference, but it should not be much. So like in this case, if we rounded this, it would be 0.017, which is what we got, but it's just slightly different. Just so that you know that and don't think that maybe you've done it wrong if you get something a little different. But this is a good way to, check and make sure that you did it correctly, and get, the p-value from your calculator. So there's this method of doing it. You do need to know how to do it by hand. Like I do want you to know how to go to your chart and be able to figure out the area, and know that that is your p-value. But this is also nice because like in the real world, you're not sitting there computing these things by hand. And I think it's important that we stay practical in that, and that you would never be in a job situation and not just use like a calculator or a program of some sort to calculate these things. But it is important that you know where they come from, because that way you're better able to understand it. You're not just saying, oh, I know this is the p-value. You can actually say what the p-value is. Like you could say the p-value is the area in this tail, which is important for understanding. I'll tell you, when I first started programming, I did not know what the p-value was. Like I could tell you like how to decide to reject the null or not, but I didn't like conceptually understand. So it's always good to know. Okay, that is it for my little demo here. So I'll stop, or actually, no, I won't stop sharing. I'm just gonna minimize this. Okay. So now that we did this example and the demonstration, I want you all to try this one on your own. So this says a survey by Men's Health magazine stated that 14% of men said that they used exercise to reduce stress. Use alpha equals 0.10. A random sample of 100 men was selected and 10 said that they used exercise to reduce stress. Use the p-value method to test this claim. Okay, so I want you guys to attempt this one on your own. I'm going to give you a few minutes because I know these take a while. So why don't you work on it? You can do it. I would recommend doing it by hand, but you can definitely use your calculator to check. So I would do both. Do it by hand and with your calculator. And then why don't you private chat me what you get as your p-value? Actually, no, don't do that. Private chat me if you can reject the null or not. That's a little easier. So I'll give you a few minutes. Send me a private chat when you're done telling me if you were able to reject the null or not. All right, I'm just gonna give like another minute to keep working. Just chat me if you think you can or can't reject the null when you're done. Okay, let's go ahead and talk about this one. All right. All right, so step one is to state our hypotheses and identify which one is the claim. So first of all, let's do our null hypothesis, which is H naught. And this is always P is equal to whatever that proportion is that we're talking about. So the proportion that we're talking about is 14% or 0.14. So that is P is equal to 0.14. Our alternative here is going to be P is not equal to 0.14. And in this example, it says that the survey states that 14% of men use exercise to reduce stress. So that's the claim, because we're using this hypothesis testing to test the survey's claim. Okay. All right, so let's go ahead and compute the test value. So once again, I'll write down the formula. It's Z equals P hat minus P over the square root of PQ divided by N. Okay, so now we just need to figure out what each of these pieces is based on the information we're given. So P hat is going to be the sample proportion. So that means that we're going to look at this sample that was taken. So the random sample is 100 men, and 10 of them said they did use exercise to reduce stress. So P hat is going to be 10 over 100, because that is the proportion of our sample that said they use exercise to reduce stress. This is equal to 0.10. Okay, so now we need to identify P, and P is just that proportion that's given in your hypotheses. So this is 0.14. Q is always 1 minus P, so this is 0.86. And then N is just going to be the sample size of that random sample, which in this case was 100. Let's plug all this in and we get 0.10 minus 0.14 over the square root of 0.14 times 0.86 divided by 100. All right, if I plug this into my calculator, I get negative 1.15. All right, so I'm gonna draw my little thing here, and right here goes negative 1.15. So I want to know what's in this tail. So if I come to my chart here, negative negative 1.15, and that area associated is 0.1251. And let me make sure, because I'm now thinking I may have made an error when I did this earlier. So give me a minute before I accidentally say something that's incorrect. So 1 second. Okay, yeah, when I did this earlier, I was not thinking about the fact that this was a two-tailed test. So I was just saying, like, oh, we're only concerned about this tail. But because the area in this tail is 0.1251, but we're doing a two-tailed test, we need to multiply that by 2 to find the p-value. So I said that in my lecture video, that if you have a two-tailed test and you find the area in one tail was 0.1251, in order to find the p-value, you need to do 2 times 0.1251. And I did not do that when I did this problem earlier because I was not thinking about it. It doesn't change the answer, but I just realized that I needed to do that. So this is 0.2502. All right. So in order to decide whether we reject the null or not, we look at the p-value and how that relates to sigma, or our level of significance. Well, 0.2502 is definitely going to be bigger than 0.10. So unfortunately, that means that we cannot reject the null hypothesis. So what does this mean in terms of a summary? This means there is not enough evidence to reject the claim that 14% of men use exercise to reduce stress. Okay, that's it for section 8.4. So yeah, that concludes 8.4 and how to do the z-test when you're dealing with proportions. Oh, yeah, so in order to reject the null, you want the p-value to be less than. So let me go back to my lecture notes that I posted. I guess it's not written here. But in order to go ahead and reject the null, you want the p-value to be less than the null hypothesis. And in our, you want the p-value to be less than the significance level. And in our case, our p-value was significantly greater than that because our alpha was 0.10. So you want it to be less than. Okay, that's everything for 8.4. I'm going to move on to the next section that we're going to cover, but I just ran out of water. So I am going to go refill my water bottle and come back and keep going. I'm going to, I don't know, have a nice 2-minute break while I go get some more water. So I'll be right back in a second. Okay, so this will definitely ring a bell because some of your projects that you're doing look like this, where you're saying, oh, like here are two means. Is there like a difference between the two of them that's significant? So we skip section 9.1 though. 9.1 talks about the difference between two means, but the reason we skip it is because it uses the z-test, which we've talked about the z-test for means, and we've said, well, the z-test for means has to use the population standard deviation. And like we talked about, that's probably not too realistic. because most of the time you don't know the population standard deviation. So it's a little more like theoretical. The t-test is really more applicable to real life scenarios because usually you don't know the population standard deviation. I mean, it's kind of interesting if you think about it because like you're making a claim about the population mean, but you know the population standard deviation. Like it's just a little like theoretical. So the reason that we skipped 9.1 is because of that. So we're just going to jump right into 9.2, which is testing the difference between two means of independent samples when you don't know this population standard deviation, which happens more often. So skip 9.1, you don't need to know it. It doesn't make a whole lot of sense to cover it. So we're just going to start at 9.2. So now instead of just doing testing on if the mean is equal to something, we're going to be doing testing on two means if maybe there's like a difference between them. So like this says, many times the conditions set forth by the z-test cannot be met. So it's more theoretical. We typically don't know the population standard deviation, and in these cases, the t-test is used. And it's used to test the difference between means when the two samples are independent and when the samples are taken from two normally or approximately normally distributed populations. Okay, so we've been doing a lot of testing. This shouldn't look too different from stuff that we've been doing, except for, we're testing two means now, not just one. So let me put this up. So let's go ahead and write down what the formula is for the test value. Go ahead and do that. So this is T equals, and this one might look a little more complicated, but it's only because we're dealing with two means and two different samples. So we have a little bit more in our like formula to calculate this. So x1 bar minus x2 bar. And the reason we have x1 and x2 is because two different samples. Minus mu1 minus mu2 over the square root of s1 squared over n1 plus s2 squared over n2. Okay, so I want to briefly explain what all these things are in this formula. So x1 and x2 are going to be the sample means of your two different samples that you have. So x1 bar being the sample mean of your first sample and x2 bar being the sample mean of your second one. We have mu1 minus mu2, but I'm going to explain this when we hit our first example because mu1 minus mu2 is 0. Whenever there being no difference in the population means is hypothesized. In all of the examples that we're doing, this quantity right here ends up being 0. I think it'll make more sense once I write out the null and alternative hypotheses, but just know that if we have in our hypotheses that there's no difference between the population means, then that's going to be 0. And then down here we have S1 squared, which is the sample standard deviation of the first sample squared, over N1, which is going to be the sample size. And then you add that to the same thing for the second sample. But if you remember, whenever we do a t-test, we have this thing called degrees of freedom that we use. And now this kind of like brings up an interesting point, because if you have two different samples, what if they're not the same size? Because whenever we would do degrees of freedom, we did one less than the sample size. But what if you have two samples and they're two different sizes? How do you decide what the degrees of freedom are? I don't know. So what we do is they are equal to the smaller of n1 minus 1 or n2 minus 1. So basically you figure out what the degrees of freedom would be for each of these samples separately, and then you take the smaller of the two. So that's how we deal with that. And then it says right here, we will use table F to find our critical values and our p-values, which table F is just the one for the t-distribution, which makes sense because we're doing a t-test. But there's something really important that I need to specify before we get into this. Your calculator will perform a two-sample t-test. There's an option in there to use two samples and to do a t-test. There's even an option to do a two-sample z-test. Your calculator is totally capable, but it uses a very complicated formula to determine the degrees of freedom. So instead of using the smaller one of n1 minus 1 or n2 minus 1, you'll notice that is not at all what it uses for degrees of freedom. I don't even know what complicated formula it uses to decide it, but it's not even close to accurate. So just for fun, I went to do an example in the calculator, and the degrees of freedom were supposed to be I don't even know, maybe 19, and my calculator said it was 29 point something, it's a decimal. So I don't really know what it uses to do that, but that's going to affect how the calculator gives us answers. So I am not going to do a demo using the calculator for these problems, just because of that, because it does not use the right degrees of freedom. So just so you know, that's why I'm not doing any calculator demos for this one, even though it's fully capable. But that's my warning. Don't do it because you're not going to get the right answer. So just don't use your calculator. We're just going to forget it for this one. Okay. With that being said, we can just go ahead and do an example. So our example here is, oh, well, I guess I should say this. The first example that we're going to do, we're going to do without p-values. So we're going to do it the traditional way. And then the second example we'll do with p-values. I just got a question in the chat. No, I did not cancel the quiz this week. It's take home, and I'm posting it tonight, and you'll have 3 or 4 days to do it. So no, I didn't cancel it. It's just not up yet, and it's not in class. All right, so our example here, this is going to be using the traditional method, and then our next one will use the p-value method. So a real estate agent wishes to determine whether tax assessors and real estate appraisers agree on the values of homes. A random sample of the two groups appraised 10 homes. Is there a significant difference in the values of homes for each group? Let alpha equals 0.05. So you might recognize some of this wording from your research questions. Is there a significant difference? Hence why I had you word your questions so specifically. So here it is. So anyways, we have some information given. Whenever I convert it to a black background, it leaves some things out. So this should be X1 bar. This should be S1 and N1. This should be X2 bar, S2, and then N2. So we have a sample mean for the prices of homes for the real estate appraisers, and then we have the sample standard deviation, and then also the number of homes that were in this sample. And we have that for both the real estate appraisers and the tax assessors. Okay, so our first step is to state our hypotheses and identify which one is our claim. So this will look slightly different than when we've been doing our null and alternative hypotheses in the past, but it's not too different. So our null hypothesis is going to be that the two means are equal, the two population means. That's because it says a real estate agent wishes to determine whether they agree on the value of homes. So all we're trying to see is if they are different or if they're the same. So we're going to have our null hypothesis be that the population mean of group 1 is equal to the population mean of group 2, which would mean that they appraise them the same. And then our alternative hypothesis is, is going to be that mu1 does not equal mu2, that there is a difference between the way they appraise the homes. All right, so our step 2 is going to be to find the critical values from the appropriate table. So first, let's write a few things down that we need to do this. So our significance level is 0.05. Note that this is a two-tailed test. And then remember, the degrees of freedom are going to be the smaller of n1 minus 1 and n2 minus 1. N1 minus 1 is 9, and N2 minus 1 is 9. So they're the same, which means that the degrees of freedom is 9. If they were different, we would have taken the smaller of the two. All right, so we have to use our chart to figure out what the critical values are. So let's come over to our t distribution. All right. So our degrees of freedom are 9. So I'm going to circle that one. We are doing a two-tailed test. Yeah, two-tailed test, and the level is 0.05, which is right here. So if I see where these meet, that means that my critical values are 2.262 and negative 2.262. So it's plus and minus 2.262. Like usual, I'm going to draw a nice little chart. And then I'm just going to shade this in. And this is our critical region. Remember, we're doing this the traditional way. So if our test value falls within the critical regions, we reject the null hypothesis. And if it does not, then we don't reject it. So to do that, we have to compute the test value. And this is t equals x1 bar minus x2 bar minus mu1 minus mu2 over the square root of s1 squared over n1 plus s2 squared over n2. All right, so let's fill some things in here. So our x1 bar is going to be the mean from our first sample, and that's given to us as 83,256. And then we need x2 bar, which is given here as 88,354. And then we would have minus mu1 minus mu2. But if you remember, I said at the beginning, if our, oh, I didn't actually write it, I just said it. If our hypothesis says that mu1 equals mu2, that means that that is going to be 0. So because in our hypotheses we have mu1 equals mu2, down here we subtract off 0. So this quantity right here is just 0. And I think in every example that I will probably give you, and in the examples in the notes, this will be 0. So just letting you know, in all the examples that I'm going to do, this will be 0. And then this goes over the square root, and we do the standard deviation of the first sample, which is given as 3,256. And we square that and divide it by the size of the sample, which is 10. And then we do this for the next one. So the standard deviation of sample 2 is 2,341, and we square that and put it over 10. So now we just need to plug this all into the calculator. And we get negative 4.02. Okay, well, negative 4.02 very clearly falls within the critical region. It's somewhere over here, and that means that we are able to reject the null hypothesis. All right, and now all we have to do is summarize the results. So this means that there is enough evidence to support the claim that there is a significant difference between the values of the two groups. This is explaining why that is. It's because we've rejected the null hypothesis, and the null hypothesis says that these values for each group were equal, but it said the means of each population were the same. But we were able to reject that, so we can accept the alternative that there is a significant difference between them. Yeah, so I mean, so in terms of like knowing when you can reject and when you can't, I would definitely say that's something to put on a cheat sheet for the exam for sure. I can totally write something up though. So you really just need to know when you can reject if you're doing the traditional test, which is what I just did, or if you're doing the p-value test. So yeah, I can definitely like write something up or make like a little flow chart or something. Which I would recommend you put on a cheat sheet because hey, I'm giving you a cheat sheet for the exam. You may as well use it, right? So yeah, let me just make a note to do that and I will make one.
What about, because I have like the actual physical copy and this thing right here, they give you like a key thing that tells you like all the formulas and it gives you like all the charts that you need.
Mhm.
We use that or no?
Yeah, you can use that. That's totally fine with me.
Nice. Thank you.
Yeah, I'm okay with you using the charts that are in the book because you need the charts in the book. So if there's like a little thing with like all the charts on it, that's fine. Like I said, in the real world, you're not like, it's not like you can't use these things. So it doesn't bother me that much. My biggest thing is that you know how to apply them. And if you don't know how to apply them, they don't do you any good. So totally fine. Okay. Let's do one last example for today, which is just going to be another example of doing this testing between two means. So we'll just do one more, and I'm going to use the p-value method, and then we will call it good for today. And I know that there's another page of notes after this. It's on confidence intervals for two means. I am trying to decide if I want to do it or not. Because there was a section in the book for hypothesis testing with confidence intervals, and we didn't do it because it's not part of like the summer curriculum. So I'm trying to decide if I want to even do this part. I'm not sure yet, so we'll see on Thursday. But I'm not going to do it today. Yeah, good. So I got a private chat. We did reject the null because the t-value fell within the critical region. Yeah, so you've got like the two methods that you can use. So you can either do the traditional method, which says I find the critical regions, and if my test value is in the critical regions, I can reject. If it's not, I cannot reject. Or you do the p-value testing, which is I calculate the p-value, and if the p-value is less than alpha, then you can reject. So I know that's a lot, so I can definitely make like a little flow chart with like things on it. Especially because it's like you have t-testing and z-test, but then you have like two types of how to decide whether to reject. So like, yeah, there's a lot going on. Okay, yeah, flow charts are very helpful. I wish the book would like make a nice flow chart, but I could. Okay, so let's do this last one. So a researcher suggests that male nurses earn more than female nurses. A survey of 16 male nurses and 20 female nurses report the data below. Is there enough evidence to support the claim that male nurses earn more than female nurses? Use alpha equals 0.01. Okay, once again, my thing cut off like some of this. So this should be x1 bar, s1, and n1. This should be x2 bar, s2, and n2. If you have the version of the notes with the white background, it shouldn't be cut off. Okay, so let's state our hypotheses here. So first of all, we are claiming, or our researcher is suggesting, that male nurses make more than female nurses. Okay, so that is going to help us write down our hypotheses. So for our null hypothesis, it's going to be that the means are equal. And then for our alternative, it's going to be that, let's see, males make more than females, so mu1 is less than mu2. And this is going to be our claim. Because our researcher suggests that male nurses earn more than female nurses, which would mean that the population mean for the male nurses would be greater than the one for the female nurses. Okay. So now we're going to compute the test value. I'm going to do the p-value method here. So for the p-value method, you just need the test value and then whatever your p-value is, and then you can make your conclusion. So in both methods, the traditional and p-value, you have to compute the test values. But then in the p-value one, you just need p-value, and in the traditional one, you just need your critical regions. Okay, let's compute this test value. So t is equal to, I'll write down the formula one more time, x1 bar minus x2 bar minus mu1 minus mu2 over the square root of s1 squared over n1 plus s2 squared over n2. Okay, so x1 bar is 23,750, just based on the chart. X2 bar is 23,900. And because in our hypotheses, we have the claim that mu1, or we have one of them that says mu1 is mu2, that means that, again, this value is just going to be 0. Like I said, I don't think I'm going to give you anything where that quantity is not 0. If I do, I will teach it in lecture, but as of right now, I'm going to stay away from it. I would never just throw something on the exam that didn't use 0 there. That's all I'm saying, is that I would never not teach it and then throw it on the exam. Not cool. So anyways, our standard deviation of our first sample is 250. So we have 250 squared over 20, because the sample size for that one was 20. And here's a good example where we have two different sample sizes. So when we go to find the degrees of freedom, we'll have to pick the one that is smaller. But we're not there yet. So the standard deviation of the second sample is 300. So we do 300 squared over 16. That's the sample size there. So let me plug this into a calculator. Okay, and I get a value of negative 1.60. All right, so now we have to determine our p-value here. So I'm going to go ahead and once again draw distribution just so you can see here. So our p-value, remember, is the area in our tails. But this is only a one-tailed test here, not a two-tailed test. So we only need the area from one tail. So if I have my negative 1.60 here, I want this area. So in order to do that, we have to go to our handy dandy chart. And our chart is going to give us, if you remember from my lecture video, when we're doing the p-value with a t-test, it doesn't give you the exact value. It gives you a range of values. So it'll give you a range that the p-value falls between, but it doesn't give you an exact one like the z-test does. But to use our chart, we need to remember that we have one tail, we have alpha equals 0.01, and then we also need our degrees of freedom. And if we look up here at our data, so the degrees of freedom is either going to be, it's either going to be N2 minus 1, which is 16 minus 1, or it's going to be N1 minus 1, which is 20 minus 1. And it's going to be the smaller of the two. So the smaller of 19 and 15 would definitely be 15. So our degrees of freedom are 15. And using this information and our test value, I'm going to come to our chart here. Okay, so we have degrees of freedom being 15. And then let's see, we have our one-tailed test with so one tail here, and alpha is 0.01. So there's that. But what we want to do is come to this row and see where our test value falls between. So we had a test value of negative 1.6, but for the sake of looking on here, you can just look for 1.6. So if you come in this row, you can see that 1.6 falls between 1.34 and 1.75. So what that means is that our p-value is going to fall between 0.10 and 0.05. And I went over how to do this in the lecture video. So if you haven't watched it yet, this is not like brand new. There is like a little tutorial of me teaching how to do this. So our p-value falls between 0.05 and 0.10. Oops. So that's what we know. And based off that, we have to try and decide if we can reject the null hypothesis or not. So our significance level, our alpha, is 0.01. And if we were going to reject the null, we would need our p-value to be less than 0.01. Okay, but looking at the range for our our p-value is either greater than, well, our p-value is greater than 0.05, and it's less than 0.10. But for sure it's greater than 0.05, and already 0.05 is bigger than our alpha. So we can completely say that we can't reject the null because our p-value is for sure bigger than alpha. Even though we only have a range, anything in that range is bigger than alpha. So for sure, p is bigger than alpha, which means we cannot reject it. So in terms of what that means, that just means that there is not enough evidence to reject that they make the same amount, that the means are equal. Or in other words, there's not enough evidence to accept the claim. So there is not enough evidence to reject. I'm going to phrase this differently. To accept the claim. Let's see. Our claim was that male nurses make more. So there's not enough to accept the claim. Male nurses make more than female. And that's because we were not able to reject the null hypothesis, and the null said that they make the same. And if we were able to reject it, we could accept the alternative, but we don't have enough evidence to accept it. Okay, that is going to finish us up with this section, or not, well, I say that. I'm not sure if I'm gonna do the last part of this section. I'm gonna think about it. Yeah, so I'm not sure right now. But are there any questions on the stuff that I did today from this section? Okay, let me stop sharing. Well, let me stop recording.